Yes, sir. Visible, sir.
Okay. What about Abhinay? Can you able to see this PPT file? Okay. Okay. Today we are going to discuss about the simulation of wavelength division multiplexing. Also in your syllabus, a study of WDM using some specialized software is there. So that today we are going to discuss about what are the characteristics of wavelength division multiplexing using Optisim software. Here the title is study characteristic of wavelength division multiplexing. Here by the use of WDM, that is wavelength division multiplexing, multiplexer and demultiplexer. This is an experiment for to determine uh, insertion loss of each channel of WDM multiplexer and loss uniformity. Okay, the next one to determine the crosstalk in adjacent channels of optical wavelength division multiplexing technique. We are using this the demultiplexer for different wavelength. So we are going to do the experiment for to determine insertion loss and also determine the crosstalk. Okay. Here just one small introduction about the wavelength division multiplexing, the WDM. What is mean by WDM here? Here we are using the device in this experiment. We are using the devices called WDM multiplexer and WDM demultiplexer. Here the WDM multiplexer is used for to determine the insertion loss of each of this channel. Okay. Here the next one WDM DMUX. The WDM DMUX is used for to determine the crosstalk in adjacent channel of optical wavelength division multiplexing DMUX for different wavelengths. Already you know how to give the different wavelength using CW laser. Okay. Here WDM multiplexer is a device that combines a set of different wavelengths propagating in different fibers connected at the input ports of the device into one output fiber. Already you know very well, more number of inputs and one number of output. It's called the multiplexer. The same procedure for this wavelength division multiplexer. It is a device. It combines a set of different wavelength. For example, different wavelength is different. We are applying different frequency in terms of lambda 1, lambda 2, lambda 3. In this manner, you connect or propagating with the different fibers to the input port of the WDM mux. Okay. Similarly, what is the characteristic of WDM DMUX it is a device. It's a multiple number of output input and okay, it gives one output. So the WDM demultiplexer is a device that separates different wavelength propagating through a single fiber into separate fibers. It's a multiples to single in this manner. Is a demultiplexer concept. These devices are very important components in a wavelength division multiplexed fiber optic communication systems. Okay, so in such a system, the different wavelengths carry independent informations, and all the wavelengths use the same fiber to propagate from one terminal to another terminal. Okay, so that you will get the at the time of same transmission fiber, which results in an increased capacity of the fiber optic link. For example, if there are four wavelength channels, each carrying a bit rate of 2.5 GB per second, then when you go for multiplexing, when multiplexed into fiber link, the fiber link would be carrying a total capacity of, because four wavelength channels are there, each are having bit rate of 2.5. Okay, so it's a product of four channel bit rates, not product, combining sum of four channel wavelengths. It's a 10 GB per second. For example, one wavelength carrying bit rate 2.5 GB per second. So four wavelengths they are propagating through one single fiber optical link, so that we are getting 10 GB per second. So larger number of multiplexed channels having increased capacity of the communication link. This is the concept of this wavelength division multiplexing in optical fiber optic communication system. Okay, this refers the diagram shows the transmitter, a receiver with the channel. The channel is a transmission medium. Okay, the left hand side, the wavelength multiplexer there. In right hand side, wavelength demultiplexer. Here, the transmitter. Here, the transmitter denotes your CW laser. Understand? Okay, here, this is the transmitter. Lambda 1, lambda 1 and lambda 2. Here it's a transmitter lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. It denotes your CW laser. This is a laser source. It gives the individual signals. Okay, what are the individual signals are given here? Applied to your wavelength multiplexer. Here, this is your multiplexes mixed signal through the medium. It is optical fiber cable. The multiplexed signals are transmitted over one main transmission line. It is called as optical fiber cable. It's a receiver side demultiplex signals at lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. For example, this experiment for lambda 1, for example, you choose 1510 nanometer is a lambda 1, and lambda 2, 5530, 550, 570, etc. In this manner, you just combine the different wavelength channels combined to apply the input to the wavelength multiplexer. That is a WDM 4x1 multiplexer. This is your cable, optical fiber cable. Here, the at the receiver end, we are going to use the wavelength demultiplexer. We can separately get the different wavelengths carrying optical fiber output. Okay, these are at transmitter side. Multiple optical transmitters there, each emitting at different wavelength, individually send signals, and these signals are multiplexed by a wavelength multiplexer. Here, at the receiver side, the signals are demultiplexed by a wavelength demultiplexer and also sent to multiple receivers here. These are WDM is nothing but a wavelength division multiplexing, and is now one of the most widely used technology for high capacity optical communication system design. This is one of the operating characteristic. Yeah, the wavelength division multiplexer or demultiplexer is characterized by some important characteristic. This includes insertion loss and crosstalk. And what is insertion loss? What is crosstalk? Here, the insertion loss is calculated with this experiment is if P1 is power entering the mux at a specific wavelength. For example, lambda 1, the power entering means for applying 200 watts. This is called as P1. Okay, then, and the P2 is a power exiting from the mux. Then the insertion loss of mux at this wavelength is defined by IL is nothing but insertion loss in terms of dB equal to minus 10 log of output power divided by input power. That is where power exiting from the mux, and also P1 is power entering to the mux. In this way, by using this formula, you can calculate insertion loss. Okay. Then what is crosstalk? In wavelength division multiplex system, the same fiber is used to transmit more than one wavelength. Okay, because of the crosstalk is occur. Also, due to design of fabrication errors and a small amount of power at other wavelengths may be also exiting from the same output port. So this referred to a crosstalk. The crosstalk calculated by using the formula, and also it can defined by CT is nothing but crosstalk in terms of dB. Here 10 log, here some mistake is there. Here no negative sign here. 10 log of PJ by PI. Here PJ is okay. Okay. Here where PJ is the unexpected power and PI is the expected power. Okay, let us see at the time of calculation, the crosstalk is coming with negative or positive. Normally, PJ is nothing but unexpected power, and PI is nothing but expected power. In this manner, you calculate the crosstalk and insertion loss. These are the operating characteristic of wavelength divisional multiplexing technique. Here, now we are going to simulate a WDM system with 4 channels to find insertion loss of multiplexer channel, and also measurement for optical crosstalk in WDM DMUX. Okay. Here, what are the components required for this simulation? First, you need CW laser, that is a laser source, 4 number of laser source you need, and multiplexer 4x1 1, and WDM DMUX 1, optical power meter, and optical spectrum analyzer. First, we are going to see first experiment called to find the insertion loss of mux channel. Okay, this is the diagram. Just you need to draw by freehand sketch. Just you take it as note for the simple diagram to find out insertion loss calculation of each channel of WDM mux. For that, you need 4 CW laser for propagating 4 different wavelength channels. Okay, here you need to get the WDM mux 4x1. Just you find components area. Just you type this one, WDM multiplexer 4x1. At the receiver end, at the output of WDM mux, you connect one optical power meter and one optical spectrum analyzer. Here, the first laser source contains frequency of 1510 nanometer, and power is 210 watts. Kindly note it down, this one, CW laser 1, 2, 3. Based on that, you just change the parameters and do the experiment to find out the insertion loss calculation of each channel of WDM mux. First frequency is 1510, 530, 550, 570. Okay, the power is in terms of watts. Don't forget to select the units. Okay, here nanometer, here watts. Okay, power 210 watts. This CW laser 1, power 205 watts. CW laser 2, power is 190 watts. And final laser 3, so 180 watts. You can easily remember 1510 and 530, 550, 570, 210, 205, 190, 180. In this manner, you calculate. Okay. Already you know very well how to change the frequency and power in each and every source, laser source. Here also, double click on that. Just you select the channels. Insertion frequency at all the channels 10, 30, 50, and 70. Okay, at the receiver side, you connect one optical power meter, one optical spectrum analyzer. Okay, this is the insertion loss calculation table. Here, already we find with we found that this one wavelength 1510, 30, 50, 70. Here the input power, that is your P1. The also called as optical power without mux. Okay, 210, 205, 190, 180. What we applied here, 210, 205, 190, 180. In this manner, you set the power, optical power. That is called also called as input power or without mux optical power. So, by the use of optical power meter like this, just you calculate the for wavelength 1510, 104.99, 64.73, 75.42. In this manner, we calculate. By using the formula, we find out the insertion loss. This is a simple experiment. Okay. Next, this is a snapshot of this finding insertion loss of calculation of each channel of WDM mux. Okay. Here, 2 optical power meters are placed here. One is for to find out the input power. This the optical power meter shows that the input side what we apply power 210 watts. Here also 210 watts is there. Here the output section we are getting 104.989. Let's see 104.99. In this manner, you need to connect the optical power meter and also observe the optical spectrum of each and every wavelength carrying signals. Okay. Here you need to change one more thing. Here, when you click on the WDMX, in one option is there, insertion loss option. Just you put 3 dB. You are getting the 3 dB spectrum. Okay. So also you need to connect. If you want to find the table for 1010 means 1510, you need to connect. You need to set 1010 only. Then only you will get this optical power meter. If you're not selecting means all the combination powers, for example, 210, 205, 190, 180 combination will almost 900 something. Total power is coming here. So don't forget to click this option as 1000 because we are using 4 channels, 1, 2, 3, 4 channels. It also gives mentioning 4 frequencies, 0, 1, 2, 3 and all. Okay. So what is your input? 1510. So you set the frequency for the WDM multiplexer all with this frequency 1510. Then only you will get the optical power meter. Otherwise, you will get all the sum of powers you will get at the output side in optical power.
Excuse me, sir.
Yes.
Sir?
Yes. Tell me.
Sir, that 1010 or 1510, sir. That one.
Which one?
Frequency, sir. 1510 or 1010, sir. NM.
1510. 1510.
Okay, okay.
1530. Now we can easily think, right? 1510, 1550, 1550, 1570. Okay, clear.
Sir, I'm asking at the mux, sir.
Mux
At
means
the multiplexer, all 1510 only, sir.
if you want to find out first table, for example, this is a calculation for finding the wavelength for 5000, 1510 means here the input is 510. You need to get this one. At the time of simulation, we will get clear. Okay. Okay. I will tell the procedure how to do. Okay.
Okay,
Then
okay.
next one, crosstalk determination of each channel of WDMX. Okay. Here the same thing. The same 4 inputs are there. Only change is you replace mux with demultiplexer. In this output section, you need to connect optical power meter and optical spectrum. Okay, for each and every channel you need to get. For example, I am connecting 210 watts input. I am getting 21 nanowatts. 21 nanowatts are getting e power minus 9. Okay. Also, we are getting the optical spectrum with 1.51 wavelength. That is nothing but 1510 nanometer wavelength. So that we are getting optical spectrum as this one. Okay, let us see with simulation file. And also, this is the calculation table for the crosstalk measurement of each channel of WDM DMX. Here, the same table, wavelength in 1510. Here, you need to calculate P1, P2, P3, P4. P1 is nothing but 1510 nanometer channel. What is the values are getting? Okay, these are, for example, 1510 wavelength crosstalk. How you find out means, for example, 1530 channel by using the formula P2 by P1. Because we are here P1, all the values are with respect of P1. Here P1 is nothing but this one, power 1, 210, because this is your reference watts, reference power. So that we are calculating this one by using this formula. For if you want to find the crosstalk for 1510 nanometer, in this table means for 1010, it's the input power is your 210. 1530, the power is by using the formula you calculate P2 by P1. For example, we are getting 21 nanowatts divided by your 210 watts. Based on that, you calculate this crosstalk. Okay, similarly, by using the formula for 550 10 log P3 by P1. P3 by P1 value. This is P1 is nothing but here 210. 210 is your P1. So that you using the same formula you find out 1570. Okay, then second table for 1530 nanometer crosstalk. Here this is by using the formula. Here the 1530 is a P2 reference power. So that you used to get the by using the formula you calculate crosstalk for this one. Similarly for 1550, 1570, Each and every channel you need to find out. How you can how you calculate. This is your input power. The same way you calculate all the powers, all the channel powers. You can observe the optical spectrum of each channel. Okay. For finding the second experiment, you just connect. Replace this option. You connect the second one, 1530. Then after finishing calculation, 1530 nanometer, just you connect for 1550. So each and every tabulation, you need to remove this source. You connect with what you are finding, 1550 or 1570. In this manner, you change the inputs. Then observe the optical power meter output and also observe the spectrum by using this formula. Just this file, I will circulate through chat box. You download this file for easy calculation. Up to this, anyone having doubt means you can ask for finding measurement of crosstalk and for insertion loss. Up to this, anyone having doubt? Okay, let us move with simulation. Okay, this is your insertion loss experiment file. Here I am using 4 sources. This is experiment 3. This is experiment 3, insertion loss. Here I am selecting the frequency. First one, 1510 nanometer. Here frequency 1510 nanometer and the power is 210 watts. Okay, don't forget to select the units. Unit is nanometer and power in terms of watts. Okay, this is the first one. And second one, 1530 205 watts and the 1570 180 watts. These are inputs. Here select WDM mux 4 class 1. Okay, here double click on that. You click to find the insertion loss. You click this option, insertion loss. You select 3 dB. This is the parameter you need to change. Then another one, this is under main category. There are 5 categories are there: main, channels, ripple, simulation, and noise. Here channel also there. You need to um, click all the frequencies, frequency 0, 1, 2, 3, like that. What you are applying these inputs, it shows. I am in this here. I need to connect. I need to calculate the insertion loss at second channel. Okay, 1530. For example, in PPT, I am showing with 1510 nanometer. I am connecting input optical power, measuring the power at 1510. So that I want to now I want to check with 1530 nanometer channel. Okay, so that I am selecting all 1530. Okay, here double click just to change the parameter as 1530 530 nanometer. Okay, if we start with 1010 means here you connect optical power input, you check the what your channel, what is your applied power 210 watts means just you conclude this one. This 210 watts is power is going on to multiplexer. Then you connect output as power meter with I need to get 1530 nanometer channel only, so that you select all the values. If you go for another lesser source, insertion loss means you need to change 1550. Okay, then after calculation you connect all the, you set the all the values are 1570. In this manner you calculate, then only you will get the output. Otherwise you will get all the sum of powers can be shown in output side power, optical power meter. Okay, now I think we were getting clear. Okay, now after simulation, what is the optical input power is at 205, because we are giving 205 is our output. Here 1030. Here this is our output 102.44. This is our output. This is at 1030. Okay, 530. Okay, here if I want to change with 1550, I want to find the insertion loss at channel 3. That is lambda value of lambda 3 value of 1550. So in channels we change the values are 550. Okay, now again you run this one. Now we are getting 94.92 optical output. Okay, here you connect. I want to check with this 1005. There's a what's your value? You are getting 190 watts. I'm connecting here to find out the 1550 nanometer channel. In this manner, you just calculate the power and also observe the spectrum. Here you can see previous one. The slide shows at power at 1.5 because I'm selecting 1.5 1510 nanometer having 210 watts. Here the optical spectrum output is showing with 1.5 micrometer wavelength. Okay, if I am selecting the second one, it shows 1000. It's a 1550. In this manner, you are getting the spectrum. Okay, here you can see 1550 micrometer wavelength it shows. Okay, if I want to check with power means you change the units. Here dBm is units are there. Just you click watts, you will get this watts. In this manner, you will get the output spectrum. Clear? This is for to find the insertion loss measurement. Okay, here what you have to do, you apply the frequency and power for input channels. You select WDM max. You also double click on that, click insertion loss. You set the 3 dB channels. You select all the channels. What channel you need to find the attenuation means you select this attenuation. 1550 nanometer. Then only will get the output side with the particular channel. Okay, this is for insertion loss finding. It's the next one, crosstalk. In this crosstalk, you need four inputs. What are the frequency and powers? 1. For example, 1010 meter. Where my input is this one. Okay, for now I am running this one. Okay, 210 my input watts. The output is 21 nanowatts. Here also the our spectrum graph at 1510. Okay, if you are connecting for 1510 means you will get this spectrum at 1.51 micrometer wavelength. Here the power is applying, power is showing in terms of dBm here. Okay, so if you want to calculate another channel crosstalk means just you replace into second channel. Now you connect the input, the 205 input is showing. Then again you run. Here you can see the optical power meter output. It's showing lesser output powers. Output power in terms of nanowatts 20.50 at input power of 205. Okay, in this manner you calculate all the powers and you note down the values for 1510. What is your input power? Input power is P1. The output power is P2, P3, P4. In this manner you calculate by using the formula you calculate crosstalk. Okay, now I think you are getting clear. Okay, for 530 nanometer, here you see the spectrum. Here it shows at 0.153. 153. Okay, if you want to find all the channels in single optical power meter means just you click here, go to channels, you select all the frequency. You mention 1010, 510, 30, 50, and 70. You will get combining spectrum of the channel optical crosstalk channel. Okay, optical to find out the crosstalk of each and every different wavelength channels. Okay, I think you are getting clear. If there is any doubt, means you can ask. Otherwise, you do the experiment, you share your screen, you show the output to us.